test bar and dial indicator and visual alignment method. Let us begin with the session.
Let us now look at the objectives of this session. At the end of this session, you will be able to align lathe centers using the visual alignment method. Take trial cuts at end of work and check the finished diameter with a micrometer and align lathe centers. Check the center align. Use test bar with dial test indicator. The tools required for this operation are steel rule, turning tool, micrometer, feeler gauge and dial gauge. Depending on the accuracy requirements, different methods are available for aligning lathe centers. The methods for alignment of lathe centers are visual alignment, trial cut method, using test bar and dial indicator, using tailstock graduations, trial cut method. Let us now learn the sequence to align the lathe centers using the visual alignment method. Loosen the tailstock clamp lever or nut. Turn the tailstock hand wheel until the tailstock barrel extends about 25 mm. Slide the tailstock to the left until the dead center is approximately 10 mm from the live center. Turn the tailstock hand wheel until the point centers are almost in contact. Place a sheet of white paper on the lathe bed centers. Look down on the top of the centers and alignment of the lathe center points. Adjust the tailstock by means of the two screws until the points of both centers are in the same line. Tighten the loose adjusting screw to secure the part in the tailstock. Let us now learn the sequence to align the lathe centers using the trial cut method. Mount the workpiece between the center of the lathe. Performing turning operation at the tailstock end of the workpiece deep enough to produce a true cylindrical surface. The cut should be about 8 mm long. Stop the lathe and note the reading on the graduated collar of the cross slide. Back the cutting tool away from the workpiece using the cross slide handle. Move the carriage until the cutting tool is about 25 mm from the lathe carrier. Rotate the cross slide handle slowly until the graduated collar is at the same setting. Machine this end for a length of about 12 mm. Stop the lathe and measure the diameter of both the turned surfaces with vernier calipers. The lathe centers are in alignment if the diameter of the two machined sections is the same. If these diameters are different, the tailstock must be adjusted by half of the difference. This can be done by using a feeler gauge of the correct thickness between the tool point and the workpiece. Adjust towards the cutting tool if the diameter at the tailstock end is larger. Adjust away from the cutting tool if the diameter at the tailstock end is smaller. Take another light cut from both machined diameters using the same graduated collar setting for each cut. Measure the diameters using vernier calipers. Continue adjusting the tailstock until both diameters are the same. Let us now learn the sequence to align the lathe centers using test bar and dial indicator. Clean the centers of the lathe and the center drilled holes in the test bar. Mount the test bar for required height between the centers and tighten the tailstock spindle clamp. Mount a dial indicator on the tool post or on the lathe carriage. The contact point should be on the center of the bar and the indicator plunger should be in a vertical position. Adjust the cross slide so that the indicator needle registers about 1/2 of a revolution on the diameter at the tailstock end. Move the carriage to the left by hand until the indicator registers on the diameter at the headstock end. Note the indicator reading. If the readings are not the same, move the carriage until the indicator again registers on the tailstock end diameter. Loosen the tailstock clamp nut. Move the tailstock in the proper direction such that the amount of movement should be equal to the difference between the indicator readings. Tighten the adjusting screw to lock the upper part of the tailstock in place. Tighten the tailstock clamp nut and recheck to make sure that the test bar still fits snugly between centers. Repeat these steps until the indicator readings at the two ends are the same. To recap, we have learned to align lathe centers using the visual alignment method. Take trial cuts at end of work and check the finished diameter with a micrometer and align lathe centers. Check the center align. Use test bar with dial test indicator.
So that's all about checking alignment of lathe centers such as leveling, axial slip of main spindle, true running of headstock center, parallelism of the main spindle to saddle movement, alignment both the centers. See you in the next session. Hello and welcome to this session on adjustment of tool post. Let us begin with the session.
Let us now look at the objectives of this session. Set correct center height with the help of boat linear. Set correct center height with the help of fine adjustment screw. Set correct center height using packing piece. Tool post. It is mounted on the compound rest and is used to carry cutting tools and tool holders. The different types of tool posts are single way tool post, quick change tool post, and four-way tool post. Tools required for conducting this exercise are single way tool post, quick change tool post, four-way tool post, single point cutting tool, boat piece, dial gauge, and shims. Let us now learn to adjust the height of the tool on a single way tool post. Clean the tool post seating face. The tool is positioned on the boat piece and is clamped by the screw. The center height of the tool tip can be adjusted with the help of rocker arm and the ring base. Only one tool can be fixed in the tool post. The tool is clamped with only one screw. Check the center height with a dial gauge. Center height is adjusted by boat piece. Let us now learn to adjust the height of the tool on a quick change tool post. Clean the tool post and tool holder. Tool is fixed on the tool holder and brought near the center. Check the center height with a dial gauge. Center height is adjusted with the help of fine adjustment screw. Tool post has the best rigidity for holding the tool. Once again, check the center height with a dial gauge. Let us now learn to adjust the height of the tool on a four-way tool post. Clean the tool post seating face and place the shims on the seating face. Use minimum number of shims for height adjustment. Shims must be flushed with the edge of the seating face. Place the tool in the tool post on the shims with the tool butting against the wall of the seating face. Tighten the tool with the center screw of the tool post. Check the center height with a dial gauge. Remove or add shims and check the height when the tool is tightened by the center screw. Tighten the other two tool holding screws, alternatively applying the same amount of pressure. When both the screws have a full gripping pressure, tighten the center carefully. Check once again with a dial gauge. To recap, we have learned to set correct center height with the help of boat linear. Set correct center height with the help of fine adjustment screw. Set correct center height using packing piece.
So that's all about adjustment of tool post. See you in the next session. Hello and welcome to this session on mounting jobs in between centers. Let us begin with the session.
Let us now look at the objectives of this session. At the end of this session, you will be able to prepare work for turning in between the centers. Set live and dead center proper alignment. Mount the catch plate. Set the bent tail carrier. Support the job in between center. The tools required to perform this operation are facing tool, center drill, drill chuck, driving plate, live center, dead center, lathe carrier, and surface gauge. Let us now learn to prepare the workpiece for turning in between centers. Turning workpiece in between centers avoids the need for truing the work. The workpiece needs the following preparation to be carried out before the actual operations are to be performed. Face both the ends of the workpiece. Perform the center drilling operation at both the ends. Dismantle the chuck from the spindle nose. Assemble the driving plate or catch plate. Assemble the spindle sleeve to the spindle nose. Fix the live center to the sleeve. Ensure that the spindle sleeve and live center are free from damages, burrs, and are thoroughly cleaned before assembly. Check for the true running of the live center with the help of a chalk. Select a suitable lathe carrier according to the diameter of the work and fasten it on one end of the work with the bent tail pointing outwards. Workpiece that has a finished surface should be protected by inserting a small sheet of copper or brass between the end of the screw and the workpiece in the carrier. Mount the dead center in tailstock spindle. Check live and dead center alignment. Apply grease to the center hole of the workpiece to be engaged by the tailstock dead center. Move the tailstock to a position on the bed to suit the length of the workpiece. The tailstock spindle should extend approximately 60 to 100 mm beyond tailstock. Clamp tailstock in position by tightening the tailstock clamp nut. Engage the work center hole with the point of live center and with the tail of the lathe carrier in the slot in the catch plate. Ensure that the tail of the lathe carrier does not rest on the bottom of the slot in the driving plate. Advance the tailstock spindle by the hand wheel rotation until the point of dead center enters the center hole of the work with proper seating, eliminating all endwise movement. Move the tail of the carrier back and forth while adjusting the hand wheel until only a slight resistance is left. Tighten the tailstock spindle clamp at this position and check that the resistance does not change. Set the machine for about 250 RPM and allow the work to run for a few seconds. Check once again for the resistance and adjust the tailstock spindle if needed. Work is now ready for operations. Before holding the work in between the centers, ensure that the centers are aligned. To recap, we have learned to prepare work for turning in between the centers. Set live and dead center proper alignment. Mount the catch plate. Set the bent tail carrier. Support the job in between center.
So that's all about the mounting job in between centers. See you in the next session. Hello and welcome to this session on making taper turning by form tool and compound slide swiveling. Let us begin with the session.
Let us now look at the objectives of this session. At the end of this session, you will be able to grind form tool for taper turning. Turn the taper using the form tool. Turn taper by compound slide swiveling method. Select drill size for taping. Drill blind hole to correct depth for tapping. Let us now understand taper turning operations. Taper turning involves gradually reducing the diameter of a cylindrical workpiece to create a conical or tapered shape. Taper turning operations can be performed by the following methods: forming tool, compound slide swiveling, taper turning attachment, tailstock offset method. The tools required for this operation are steel rule, outside calipers, facing tool, center drill, drill chuck, drill bits of various diameters, forming tools, M6 tap set, tap wrench, lubricating oil with can. Let us now learn the sequence for taper turning by form tool. Check the dimensions of the workpiece using steel rule and outside calipers. Hold the job such that 50 mm is projecting outside the chuck. Face the one end and make center drill. Drill 8 mm diameter through hole. Turn to 14.7 mm diameter to possible length. Turn to 12.2 mm diameter for a length of 41.5 mm from the faced end. Perform step turning to a diameter of 10.7 mm for a length of 12 mm, leaving 23 mm distance from the face to 35 mm. Perform an undercut to 10.7 mm diameter at 9 mm from the faced end. Perform step turning to a diameter of 11 mm for length of 9 mm from the faced end. Grind tool blanks to make special form tools to the degrees of 9 degrees 30 minutes and 6 degrees for taper turning operations. Set the 9 degrees 30 minutes performing tool perpendicular to the work axis to form taper by plunging. Set the machine to 1/3 of RPM for form turning. Feed the tool perpendicular to the axis of the work and form taper. Set the 6-degree form tool perpendicular to the work. Form the 6-degree taper. Remove the job, reverse and hold the work. Face the other end of the workpiece so as to maintain a total length of 50 mm. Perform turning operation to reduce the diameter to 12.2 mm for a length of 6 mm. Form radius R3 at the end. Deburr and complete work. Let us now learn the sequence for taper turning by compound slide swiveling. Check the dimensions of the workpiece using steel rule and outside calipers. Hold the job such that 35 mm is projecting outside the chuck. Hold the facing tool in the tool post and perform facing at the end. Perform center drilling operation. Perform drilling operation using 5 mm drill bit to a depth of 20 mm. Using M6 tap set and tap wrench, perform tapping operation on the job for 15 mm depth. Use cutting oil while tapping. Clear the chip by reversing the tap frequently. Remove the burrs on the tapped portion. Reverse and hold the job in the chuck by using soft packing pieces, aluminium, under the jaws. Face the job at the other end and maintain the total length of 68 mm. Swivel the top slide to half of the included angle 45 by 2, which is equal to 22.5 degrees of the taper away or towards the operator as required. Turn the taper by feeding the tool with the help of the top slide. Deburr the job and do final checking. To recap, we have learned to grind form tool for taper turning. Turn the taper using the form tool. Turn taper by compound slide swiveling method. Select drill size for tapping. Drill blind hole to correct depth for taping.
So that's all about making taper turning by form tool and compound slide swiveling. See you in the next session. Hello and welcome to this session on checking taper by bevel protractor and sine bar. Let us begin with the session.
Let us now look at the objectives of this session. At the end of this session, you will be able to identify the parts of a vernier bevel protractor. State the functions of each part. List the uses of a vernier bevel protractor. Check the angles of the machined parts up to an accuracy of plus or minus 5 minutes. State the working principle of a sine bar. The tools required for this operation are vernier bevel protractor, sine bar, dial gauge, slip gauges, surface table, single point cutting tool, lathe. Parts of a vernier bevel protractor. This is one of the contacting surfaces during the measurement of an angle. Preferably, it should stay connected with the surface from which the inclination is measured. The disc is an integrated part of the stock. It is circular in shape and the edge is graduated in degrees. It is pivoted to the disc and can be rotated through 360 degrees. The vernier scale of the instrument is attached to the dial. This is the other contacting surface of the instrument that contacts the work during measurement, preferably the inclined surfaces. Two kerned locking screws are provided, one to lock the dial to the disc and the other to lock the blade to the dial. Uses of a vernier bevel protractor. The vernier bevel protractor is used to measure acute angles, that is, less than 90 degrees. It is also used to measure the obtuse angles, that is, greater than 90 degrees. It is used for setting work-holding devices to angles on machine tools. It is used for setting work-holding devices to angles on work tables, etc. Let us now learn the sequence for checking the taper by using a bevel protractor. Mount the blank on the chuck and set the tool on the tool post. Perform taper turning operation for a length of 40 mm by compound slide swiveling method. Set the angular surface of the workpiece between the bevel protractor, blade and the face of the base. Lock the blade and the inner disc firmly with the locking device. Note the position of the vernier scale with reference to the main scale. Read the degrees of the main scale, MSR, at the graduation 0 of the vernier scale. Note the number of lines in the vernier scale that coincides CVSD with a division of the main scale. Total reading is equal to main scale reading plus coinciding vernier scale division multiplied by least count of 5 minutes. Let us now understand the working principle of the sine bar. A sine bar is a precision instrument meant for setting work to machine angular surfaces to determine the angles of tapered jobs by calculation. To check the correctness of a known angle, sine bar is used based on trigonometrical function of sine theta, where sine theta is equal to opposite side by hypotenuse. The hypotenuse is the length between the two rollers of the sine bar. The opposite side is the height of slip gauges. The height of the slip gauges is built up by using the formula sine theta equal to opposite side by hypotenuse. Let us now learn the sequence for checking the taper by using a sign bar and dial gauge. Mount the blank on the chuck and set the tool on the tool post. Perform the taper turning operation for a length of 40 mm by compound slide swiveling method for an angle of 30 degrees. Set the sign bar of 100 mm length on the surface plate. For an angle of 30 degree, sin 30 equal to opposite side divided by 100, which is equal to 50 mm. Mount the taper component on the sign bar after placing 50 mm slip gauge under one roller with the other roller resting on the datum surface. Mount the dial test indicator with a suitable stand. Set the dial test indicator at one end and ensure the dial is in 0 position. Move the dial indicator to the other end of the component. If the dial indicator reads 0 at both ends, the setting is OK. If there is any difference, then the angle set is incorrect. The height of the slip gauge must be adjusted till dial reads 0 at both ends. To recap, we have learned to identify the parts of a vernier bevel protractor. State the functions of each part. List the uses of a vernier bevel protractor. Check the angles of the machined parts up to an accuracy of plus or minus 5 minutes. State the working principle of a sign bar.
So that's all about checking taper by bevel protractor and sign bar. See you in the next session. Hello and welcome to this session on matching by Prussian blue. Let us begin with the session.
Let us now look at the objectives of the session. At the end of the session, you will be able to practice applying Persian blue, blue matching the male and female taper work pieces. Blue matching is used for checking the matching of the meeting surfaces. An extremely pigmented paste applied to serve in the meeting of two elements is known as blue matching. In metalworking, the marking out operation is done by the quick drying stain. Both the marking out blue and the scraping blue may also be referred to as engineer's blue. Engineer's blue is prepared by mixing Persian blue with an oily material, example, linseed oil. Tool makers widely use Persian blue when the concave and convex of a mold are matching during final assembly. Materials required to carry out this exercise are engineer's blue, male and female parts prepared in previous exercises which needs to be matched, microfiber cloth to clean the blue matching surfaces, brush to apply the engineer's blue. Let us now learn the sequence to blue matching of the given male and female taper parts. Examine both the male and female workpieces for any burrs, dirt, oil or grease. Clean both the male and female workpieces with any surfactant like diesel to remove the oil from the surface of the workpieces. Use a fine graded emery sheet to clear the burrs from the workpieces. Use a soft bristled brush to clear away the dirt from the workpieces. Wipe and clean both the male and female workpieces with a microfiber cloth. Apply couple of drops of Persian blue over the male workpiece. Spread it out evenly as a thin layer over the surface of the workpiece. Now gently insert the male workpiece, which is coated with the Persian blue, into the female workpiece. Slightly rotate the workpiece in one direction and avoid rotating in both directions. Now gently remove the male workpiece from the female workpiece. Notice if the Persian blue has rubbed over the entire curved surface of the female workpiece. To recap, we have learned to practice applying Persian blue, blue matching the male and female taper workpieces.
So that's all about matching by Persian blue. See you in the next session.
अरे गीता, तुम मेरे घर आई ये तो बहुत अच्छी बात है। वास्तव में मुझे इंटरनेट के बारे में कई महत्वपूर्ण बातों को समझने में तुम्हारी मदद की जरूरत है।
जरूर चाचा, मैं यहाँ आपकी मदद और मार्गदर्शन के लिए आई हूँ।
देखो गीता, जब मुझे ट्रेन से कहीं जाना होता है तो मुझे बहुत मुश्किल समय का सामना करना पड़ता है। जैसे मैं फसलों की मौजूद